Example 5, we've got p, 2p comma p squared, q, 2q comma q squared as variable points on the parabola x squared equals to 4y. PQ is a focal chord with gradient m, and the normals at p and q are going to intersect at n. So the first thing that we're going to realize, right, x squared equals to 4y implies that a is actually equals to 1. So if I get a diagram out, because we've got a lot of subparts over here, okay, so part 1, we want the equation of the normal. Part 2, we want to show that n is going to be the point negative pq, okay, bracket p plus q, comma p squared plus pq plus q squared plus 2. So let's get a diagram out first and see what's actually happening. So I've got the parabola x squared equals to 4y over here. Okay, let's say I've got p, 2p comma p squared, q, 2q comma q squared, and you guys can see that my two orange lines here represent the normal. Okay, and the normal intersects at n. So to start, if we want to check out the equation of the normal at p, okay, it's pretty standard business. We've done this gazillion times already. The normal at 2p comma p squared, we obviously start by looking for dy dx, right? Obviously, after I get dy dx, which represents the gradient of the tangent, I can use that to get the gradient of the normal. Once I've got the gradient of the normal, it's just a simple y minus y1 equals to gradient times x minus x1. But we all know that the equation of the normal, okay, at p is given by x plus py is equals to 2p plus p cubed. Okay, so that's what we have for the normal at p. Okay, I'm not going to derive. If you guys need the proof for the standard equation of the normal, check back to the previous section. We've done this a lot of times. And of course, we also know that the normal at q, which is given by 2q comma q squared, this is going to be given by x plus q times y is equals to 2q plus q cubed. And of course, if you guys want to find the intersection point for n, okay, this is also something that we've done a lot. So I'm just going to skip out on this part. Once again, if you need the proof, check out the previous section. Okay, in 6.3, we've looked at a couple of these examples. Okay, the best way of finding n, okay, when we're solving simultaneously is to take equation 1 minus equation 2. And that's going to allow you, after some algebraic manipulation, to find y. After we find the y value of n and we want the x, just substitute it back into equation 1 or equation 2, but equation 1 is usually my preferred equation. Okay, so substitute y back into equation 1 and that's going to give you x, right? So in this case, I'm just going to jump ahead and I'm just going to say that n is now given by negative pq brackets p plus q, comma, p squared plus pq plus q squared plus 2. And that's all we have for the intersection point of the two normals. So if that's the case, right, if I've got the two normals, I can kind of see where n is. Part 3 now wants us to show that p plus q is equals to 2m and p times q is equals to negative 1. So if we think about this, where does this come from? Okay, so I've taken note of the fact that I've got 2 points on my parabola. Okay, I found the intersection point for n. Now, the only piece of information which I have not used in the question is where they tell us that PQ is a focal chord with gradient M. So if I come back and I check this out, right? So if P to Q is a focal chord, right? So if I join the 2 points up, okay, which looks like this, if PQ is a focal chord, it obviously passes through the point S. And in this case, where A is equals to 1, then the focus is therefore given by 0, 1. Now, if I take this, right, let's look at PQ as a chord. So part 2, we know that, sorry, this is part 3. We know that P is given by 2P comma P squared. And we know that Q is given by 2Q comma Q squared. So what I need is I need PQ, okay, to be a focal chord. And what I also need is the gradient of PQ is just going to be denoted by the letter M. Now, if I take these 2 points, okay, I know that I've also derived the equation of the chord numerous times in the past before as well, but in this case, if I do it again, the gradient of the chord PQ is of course given by rise, okay, over run, and if I do appropriate factorization here, while of course looking at P plus Q times P minus Q over 2 lots of P minus Q, the P minus Q's cancel away, leaving us with just half lots of P plus Q. So with this, right, if that's going to be the gradient, then the equation of my chord is therefore just y minus y1 is equals to the gradient times x minus x1. And if I take this and I expand, right, while looking at y minus p squared is equals to half p plus q lots of x minus half times 2 cancels away. So I've got minus p lots of p plus q left. Expand the p, brackets p plus q. So I've got y minus p squared is equals to half lots of p plus q lots of x minus p squared minus pq. So the minus p squared cancels off from both sides. And what we're left with is y is equals to half lots of p plus q lots of x minus p times q. So this right now, right, is the equation of the chord PQ. And according to the information given in the question, I need this chord, okay, to have gradient M, and I also need it to be a focal chord. So if I take this equation right now, okay, so I know that my chord PQ is given by y is equals to half p plus q times x minus p times q. If the gradient of this chord, if the gradient of PQ is given by M, then what that shows is that half lots of P plus Q needs to be equals to M, because half lots of P plus Q is the gradient of my chord right now. Okay, so if I multiply both sides by 2, that shows that P plus Q is therefore equals to 2 times M. Similarly, if PQ is a focal chord, that means that it passes through S 0, 1. Okay, so if PQ passes through S 0, 1, then what I need is I need 1, y is equals to 1, to be equals to half P plus Q times X, which is 0, minus PQ. So 1 is equals to this. That is just 0 because half P plus Q times 0, anything times 0 is 0. So in other words, if 1 is equals to negative PQ, that shows that P times Q has to be equals to negative 1. Okay, so that's what we are asked to show for part 3. So if that's the case, we then want to write down the coordinates of n in terms of m. So if I know that P plus Q is equals to 2m, and I know that P times Q is equals to negative 1 from the conditions given in the question, then what that shows, okay, for part 4, is that n, which is given by negative PQ, brackets P plus Q, PQ is negative 1, P plus Q is equals to 2m, so it's minus times minus 1 times 2m, so that tells us that the x value of n is therefore just given by 2m. Similarly, if I look at the p squared plus pq plus q squared plus 2, we need to think of this p squared plus pq plus q squared, right? I'm going to say this is equals to p plus q all squared. But if it's p plus q all squared, if I expand this, I'm going to get p squared plus 2pq plus q squared. Whereas in reality, I've only got one lot of plus pq. So if I've got plus 2pq inside the bracket now, to balance, I'm just going to minus pq from the back. And remember, I still got this plus 2. Now, p plus q is equals to 2m. So if I square it, I'm looking at 4m squared. Minus pq is minus of minus 1, so that's going to become plus 1 plus 2, so it becomes 4m squared plus 3. So therefore, the coordinates of n in terms of m is equals to 2m, 4m squared plus 3. And this is very smart because we know that n is a variable point, okay? So you guys can see, if I come back to my diagram, n is the intersection point between my two normals, right? Obviously, as p and q changes, right, then the coordinates for n is going to change as well. N is a variable point. It depends on p and q. And it's a two-parameter type locus problem because you guys can see here in the coordinates of n, I've got both p and q inside. So what part 3 is now doing, okay, is it's changing the two-parameter type locus problem into something which contains just m, and that's very easy for us to eliminate, okay? And secondly, we're only able to do this because the question tells us that PQ is a focal chord, okay? So PQ being a focal chord means that P and Q cannot move however they like. If P moves, for example, in this case, if I shift P upwards a little bit, you go, okay, if P is sitting here, But I know that PQ is a focal chord, then you guys can imagine that Q is no longer free to vary wherever it wants. Okay, if P is up here, in order for PQ to remain a focal chord, then Q now has to move to this point on the parabola. Okay, if P moves up more, Q has to move in turn. So Q becomes fixed depending on the position for P, right? If this wasn't so, and P and Q can vary according to wherever they want to be, then the coordinate for N, okay, is going to be very chaotic. And we're not going to be able to see the locus of N being traced out into anything which is orderly. So in this particular case, since I've got the coordinates of N now, okay, so that's all guided through to us by the question, which is very generous of the question, we can now take this and we can say, okay, part 5, if I know that N right now can be expressed as 2m, 4m squared plus 3, and I want to find the Cartesian equation of the locus, then x equals to 2m and y is equals to 4m squared plus 3. If I want to get rid of m, take note that if I take x and I square it, that's just going to give me 4m squared. So if I take x squared and I substitute directly into y, then that's just going to give us y is equals to x squared plus 3, and voila, that's going to be our Cartesian equation for the locus of n, as of course m varies. Okay, so that's essentially the idea behind example 5, right? It's a very good question. It's very guided, which makes it that much easier. And of course, at the end of the day, the moral of the question is when you have a 2-parameter type locus problem, you always need an extra condition. In this case, it's just that the condition is given to you by the question already. Okay, so that's why it's essentially so easy. So that being said, this concludes example 5.